Right, guys, part of our discussion, actually the end of our discussion last week was representing numbers in terms of represented with rectangular form, in polar form, and in exponential form. And this is what we looked at as a kind of conversion from rectangular to polar and vice versa. You can use this formula to change your numbers from rectangular to polar. So the most important, what we need for today is the representative of a number in this form, in polar form, plus in exponential form. I hope you understood that at the end we said a number this way can be represented in exponential form as r e to the power j theta. Something which I didn't ever emphasize then is this angle theta. If you want to write a note there, write a note. This angle theta, especially when I express the number in exponential form like this, it can never be in degrees. Never. Never in degrees. If I were you, I would write that this theta number expressed in exponential form can never be in degrees. And that never must be written in capital letters. I'm saying it in capital letters. I said it can never be in degrees. Okay, so this is the process which took us to that form of expressing number in exponential form. So what is the value of this for what we are doing today? Today we are looking at integer powers of complex numbers and so on. So what am I talking about here? There is Z1. Let's say we were requested to take Z1 to the power 2. And that 2 there is an integer. Actually, I think I should emphasize that we are looking at positive integer powers. All together? Yeah, at the moment we're looking at positive integer powers. So this, from what we know, it will just multiply this number by itself. And it's simple. You just write this thing at 1 j square root of 3 multiplied by 1 plus j square root of 3. And that will be easy and straightforward because we know how to multiply two numbers. But this kind of operation, I think, is good only for for 2, not for more than 2. For more than 2, for example, imagine that you have to take this number to power 9. And imagine yourself expanding this thing with a, 9 factors like this. Somebody there is already shaking your head. That is tedious. All together. You know, human beings are this way. In nature, human beings are like this. If you don't understand this thing about human beings, it's your problem. Human beings are naturally lazy, created lazy. This is the reason why, once they find something tedious, they will try to find an easier way of doing it. All together. Okay, so when you describe somebody as not lazy, it's because somebody is actually is industrious in this way of trying to find ways of doing things easier, creatively, and so on. And what these days people call that we must work smart. All together? Okay. Now, what is going to be at our advantage for trying to do this kind of thing? I think the first thing is to try to represent Z. In this case, we're talking about Z1. To represent this Z maybe in polar form. That's one way which is easier. But representing it this way is not very, very clear what we're going to do. But maybe the most convenient way of representing this number is to represent it in, let me use R1 there, so that I can know that I'm talking about Z1. And then J theta 1. Why am I saying this is more convenient? Now, if I now were to put Z, not really to the power 9, let's say to the power n, let me just talk about z, not z1. Let's say just z to the power n. And this z has been represented this way as r e to the power theta. I hope you remember that we said theta was the argument of the number. It was the angle which is made by the vector representing the number with the positive x-axis. Now, to say power n of this is putting that. Then you will say power n there. Then immediately, we've got two numbers there. Remember, this is a product. We've got a positive number r, and this number in exponential notation, which is e to the power theta. And then we call upon the properties of numbers like this one. If we've got xy to the power a, what is that? This is x to the power a, y to the power a. All together. Then I think you can see from what we've been discussing, always when I'm coming up with something which we know, I write it down. The reason why I'm writing down, I'm actually trying to emphasize that most of the things you learned at school, even from grade 7 or below, they are still useful here. If you forget them, you are committing suicide here. Are we together, guys? So now we are going to apply that here. So if we apply that here, it will be r to the power n. And then e to the power j theta to the power n. Then I'm coming to x to the power a to the power b. This is what we have. Our x is actually our e, natural base logarithm. Then you get this thing as x to the power a b. So what's going to happen here? This is to the power n e to the power j n theta. I could have written n j theta, but multiplication does not care about the order of the factors, so I'm writing like that. Now guys, if you compare this to what we're talking about here, if we're here with 9, we'd have that to perform this calculation. We're going to have a lot of problems. First of all, we're going to need a lot of paper to write 9 factors for this. All together. So, but now once I've represented my number in exponential form, look at what I need. I just need about maybe 1 or 2 lines. I've got the expression there. If this angle was like pi, and now I can just write here n pi, which can be 2 pi, can be 3 pi, can be 4 pi. And then if this number was elevated to power n or power 9, I can just press, if I'm ready to multiply that now by 9 times by itself, I just press in the calculator 3r, which is a positive number, power n, then I'm done. Doesn't it look economic? I'm comparing, writing these 9 factors, and comparing, putting a 9 there, 9 there, 9 there, knowing that. What are the steps involved in doing this thing? First of all, I'm given a number, z equals to x plus y j. There it is number. What I'm going to do, step number 1, I would find the modulus, where I just take the components of the complex number, the real part and imaginary part, and square them. I'm done. Number 2, I get again the coordinates there and then find theta in radians. I repeat, in radians. Then say second function tan y over x. Then depending on my x and y coordinates, this angle is either in the first quadrant, second quadrant, third quadrant, or fourth quadrant. If it's in the second, third, or fourth quadrant, then I can use what? The reference angle, where I'm taking this angle as acute. Then adjust the angle which I need for the particular number according to where the angle, the arm of the vector representing the complex number is. I think that is clear from what we did in trigonometry. Is that clear? Then the step number 3, is now to express my z in terms of r, e, j, theta. Then after that, I can elevate my number to any power, and we see what we are supposed to do here. Any questions? Any clarifications? Do you have any problems with that? Is everything clear, guys? Now, if everything is clear, then can we then take this number? Can you please, I want you to see you having written something like this number to the power 5. This one, to the power 5. Right. I think after converting the number to exponential form this way, the elevation to power 5, you can carry it out this way, get up to there. Is that right? This is what you should have got in your calculations. Now let's sort of try to interpret what's the meaning of this. This is the argument, the angle of what? Of the number. It has been multiplied by 5, which means it's bigger. Altogether. So if the angle is becoming bigger, what is the vector doing? The vector is kind of rotating. Do you see that? It was maybe like this in the first quadrant. It has been multiplied by 5. It is thrown into that, into the third or fourth quadrant. So what happens is that when you're elevating a number to a power, the argument is increased. It's multiplied by that power, which means is that then the vector looks rotating. Now rotating, what happens to the modulus? The modulus was 2. Now the modulus has been elevated to power 5. Power 5 is about 32, isn't it? So as it rotates, the modulus becomes longer. The angle becomes longer. The magnitude, the angle becomes bigger. The magnitude becomes longer. In other words, as you increase the powers, the vector lengthens and moves around the origin. I hope you have got that feel. Do you see this? Do you see it? If you want to see it, draw the number in the Argand diagram. We did that last week. Draw the number, the number Z1 on the Argand diagram. Now draw this one to the power 5. Draw the one to power 6. Draw the one to power 7. Draw the one to power 8. You will see what happens. The vector will go like lengthening, rotating, lengthening, rotating, lengthening, rotating. That sounds very nice. So what I'm trying to do, I'm giving you the geometric interpretation of elevating a number to a power, to a positive integer power. Is that all right? So last week we saw that if we're adding these numbers, it's just the same as like adding the vectors altogether. So guys, I think the explanation I've given here must help you to do any other number like this, Z2. So I'm leaving you this one for your homework, and then encourage you to go to your textbook and do some more until you feel like you have really mastered this. Any questions there? Right, let's get to the next discussion, part of the discussion. Now, the discussion is computing roots, and that is what rational powers. Let's talk about, in this case, positive rational powers. Now, let's see. Right, how do you start? I think let's start exactly the same point, whereby we can take this Z to R, E, J, theta. And the theta there is an angle in radians. All together. Now, we're not talking about rational powers. Like with our real numbers, rational powers mean roots. Like if I say power 1 over n, that's the nth root. So now, if I'm now going to say this z to the power 1 over n, I'm actually saying this r e j theta to the power 1 over n, which is exactly the same kind of operation we did before. Is that right? So now what's going to happen now? Now this is going to be r to the power 1 over n e j theta over n. All together. So now I want you to pay more attention here. I want to concentrate really, because if you don't concentrate, then you're going to be left out a bit here. You're going to be left out a bit here. Let's take a vector, or a vector representing a complex number, like let's say here. Is that looking like a vector? Yes. So let's say that number, we've got that number there. Now, I want to do something. Now, do you notice that if I rotate this vector, what angle was that? What angle was that? What angle was that? What angle was that? 2 pi. 2 pi. All together. Can those guys who say 360 correct something there? We said here what the angle is in radians. So that angle is 2 pi. That angle was 2 pi, isn't it? So now, can I write this way? I want you to accept or reject what I'm going to do here. Can I now write this equality sign? That this equality sign is valid if I write this way. I want you to approve this or reject it. Just choose what you want to do. Whether you want to say no, correct, or you say no, reject, this is nonsense. I'll put this nicely in brackets. Let's see how many people are saying this is the same number, this one and that one. Let's see those who say it's the same number. I'm one of them. I took that number at theta. To theta, I added 2 pi. I get the same number. Yes or no? Yes. Then I take that number. Sorry. Two pi. 3 pi, 4 pi. I can continue that for the whole day until the lesson is over. Then I have here j theta plus 2 n pi divided by n. Let me try to avoid using that n there. Let me use another notation for integer, that integer. Let me use k. K is actually integer. I can say k can be 1 plus minus 1, 2 minus 2, because if I take that vector again, that is minus 2 pi. Minus it looks like it doesn't matter how many number of pi's I get there. That's right. How many number of 2 pi's I get there altogether. So what can we say here? We can say now zk, k is an integer, positive or negative. Doesn't matter. Altogether. Then guys, this is what is going to give us a formula to calculate roots of complex numbers. And the roots of complex numbers, depending what value is n, if n is 3, there are going to be n 3 roots. If n is 4, there are going to be 4 roots. And representing in other ways, you can write this thing as this, that the root number k of this number, first of all, let me just specify that this k, for calculating roots, this k we run from 0, 1, 2, dash, 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 up to n minus 1. Just check. If n was 3, it will run to 1, 0, 1 to 3 minus 1, which is 2. How many roots are there? 1, 2, 3. Altogether. So now, I think the most economic way of representing this is to represent this in polar form, this way. Then we put this as the argument as theta plus 2 k pi over n. Then we can just run, first of all, take the first one by putting k0, next one by putting k1, the next one until we get to 3 over n, this n minus 1. This looks more or less like 2. Let me just correct that. Maybe it will confuse some people there. 1. Is that clear? Is that clear, guys? Please, at this moment, I'm not going to move further unless and I understand that everybody understands this formula very well. Who does not understand the formula? I'm talking about this formula. Let's see those who don't understand the formula. Don't be shy, guys. This is not a problem of being running away from, maybe you're saying, if you say you don't understand, embarrass yourself. This is not about personal esteem. This is just about understanding. Who doesn't understand the formula? 1, 2, 3, 4, 5. Thank you for not understanding. Okay, let's go over this thing again. Let's go over it again. Is it? Does everybody understand up to here? All together? Did you follow the rotations? Did you follow the rotations? Yes or no? But if you now do the rotations k times or 20 times, it should be looking like this. All together? So now I'm stopping here and saying this, as I'm changing my k from 0, if I put k0, just look what I'm going to have here. If I put k0, this would be 0, then I'm left with something more or less like this. Then for that I can calculate a complex number. Then I go to 1. This argument will change. Then I can get the next complex number. I go to 2. This argument will change. It will be 4 pi. Because it will be that remember, yeah, I think maybe that's where the problem is. Just notice that when I was rotating and getting the same number, I was not dividing, I was just rotating, isn't it? But now when I divide, I get a different argument from that one. Then which means that's a different what? Complex number. All together. So then to get all the roots, then you must use this formula. What I've done, I've just run away from this exponential form because I think this is easier to look at and to manipulate for calculation purposes. But whatever argument you get here, you can change it to exponential. After exponential, you can change it back to rectangular if you so wish. Am I making myself clear? Do you all understand the formula? Please, guys, make sure that you understand the formula. If you don't, you better stop the lesson here and understand the formula. Yes? This is the argument. This is the argument of the kth root. Remember now, an equation which has got power n, has got n roots. Now you number those n roots, 1, 2, 3. Now, this is the formula for getting the kth root.
So, I thought for a Kula function, the argument has to be in decrease.
But I've just said it now, that when you write the numbers here in in polar form, in this way, yes, it can be in degrees. But for now, because we are migrating here between exponential and that, then it's preferable that this thing must be what? In radians. Because there's no conflict, you can convert from degrees to radians, isn't it? But you mustn't rule out the situation that in situations where degrees will not apply, cannot apply, you must yourself judge that here I cannot use degrees. But in this case here, with exponential form, you are not allowed to use degrees there. Are we together? Are we comfortable? Yes? No. Sorry, come again. ZK is the same as Z to the power 1 over n. But how many values is this going to deliver us? It's going to deliver us n values. Now ZK is the value number k. In other words, if I say Z2, that will be the value number 2. If I say Z0, that will be the initial value, the first one. And then Z1, that will be the second. Z3, that will be the third, that will be the fourth. Am I making sense? Okay. So now, I think what we need to do now is to immediately get on the system and try to use this formula. And everybody must use it today for the first time and feel it. All together? Okay. Let's see what we have got here. Examples. Examples. What are the examples we've got here? This was a promise last week. I said we are going to get the 3 roots of 1. 3 different numbers which you can, these 3 cube roots of 1. 3 different numbers which you can elevate to power 3 and get 1. So far at school we know only 1. 1 to the power 3 is 1. Is there another number? In real numbers? No. So what are we having here? We're having example 1, it says, sorry, let me pick a pen there. Right, we have got Z to the power 3 minus 1 is equals to 0. So in other words, this is a cubic equation. And we expect to have 3 roots. And we know that if it was this Z was a real number, x cubed, that we have only one solution, that is 3. But now we've got complex numbers, we've got a chance to have 3 roots. Now, let's see what we have there. We have Z to the power 3 equals to 1. According to what we said there, step number 1, we need the modulus of this number. Because now what's going to happen here, this is equals to, Z is equals to 1. Writing as a complex number, we should say 1 that to the power 1 over 3. Do you agree? Now we said, first of all, we need the modulus of that z there. In this case, we are calculating the root of this, so our z is this, isn't it? We are calculating the root of this. So the modulus of that is 1. I hope everybody is with me there. It's 1 squared plus 0 squared. Calculating the square root is 1. All together. Then, number 2. What do we need? The argument of z, which will be second function 0 over 1. And you can get this thing easily without using arctan or second function tan. Why? 1 is a vector lying horizontal like this. Do you agree? What is its angle between itself and the positive axis? 0, isn't it? So this is 0. Then now, number 3, let's put this number in exponential form. 1 in exponential form is equals to 1 e to the power j that. All together. Now, if you are going to calculate now the roots of this number, you now need zk, according to that formula. Zk will be r to the power 1 over 3. Argument theta, which is 0, plus 2k pi over 3. And our k must run from 0, 1 to 3 minus 1, which is 2. So far, am I carrying everybody, or I'm leaving somebody behind? Who is left behind? You know, what we look at here, because this is 0, a lot of people can attempt to get stuck here. A lot of people can attempt to get stuck here, because somebody can try to get stuck here by saying this is what cos of 0 plus j sine of 0. So I wrote theta here. I wanted to write 0, 0. And this thing immediately gives you 1. Isn't it? Then it looks like there's nowhere we are going. You understand? But from here, now once you identify the angle, you must come here. Now then we set z0. K0. So get here z sub 0. Then we've got here cube root of 1, which is 1. Then inside there, we've got what? 0 here for k and 0 there. 0 divided by 3, 0. And then this number is exactly number 1, according to what we've got here. That's exactly number 1. Then z1, cube root of 1, argument 2 times what? 1 times pi. 2 pi over 3. What number is this in rectangular form? This is the number 1 cos 2 pi over 3 plus j sine 2 pi over 3. Now, I'm not expecting this thing to be 0. I'm not really expecting this thing to be 0. So, just check. But I suspect this angle is in the second quadrant. Can you check that? What is, you can divide 360 by 3 just to have a rough sketch to approximately easy. 360 divided by 3, what's the answer? 120. It's an angle here. Is that right? In second quadrant, is it? Okay. So let's evaluate this. I want it, let's get this number in what? In rectangular form. Evaluate it and give me the answer. Sorry, my friend. Can you take your calculator now for the first time and evaluate this and give me the answer? Right, you should by now be getting values. What are the values? Cos 2 pi over 3. We said it was, what's the value there? Minus 0,5 plus square root of 3 over 2. I think it's better to leave it like that. I think it is going to be easy to check. Are we together, guys? Now what should we do now? We should calculate what? Have we finished? Have we finished with the roots? What are we left with? Z2. Good. Let's get Z2. Now we need Z2 equals to 1. Now if we get there, we're going to multiply that by 2, that will be 4 pi over 3. Now 4 pi is 2 times 360 roughly. Why am I not doing that? I'm just doing that to roughly position the number in a particular quadrant. Altogether, I'm just applying to degrees because they're offering themselves to easily position the number. So that would be 360 times 2 divided by 3. What's the answer? Come again? 240. That is below 270. 270 is here, isn't it? Then it's there, which means that number is somewhere here. So one root is 1 is in this quadrant, the other one is there, and the other one is this side. So can we calculate that and give it in rectangular form? I'm not going to write this expansion using trigonometric values there. Write it yourself and just give me the number there because I'm running short of space there. Can you do that? I'll give you some 2 minutes to calculate it. And watch out. Watch out. Think about conjugates. At that point, as you calculate, think about conjugates. Did you hear what I said? Okay. Sorry? Because it's minus 0,5. Minus J square root of 3 over 2. What are you seeing there? What are you seeing there? I'm seeing conjugates. If you are not seeing conjugates, then maybe it's the first time you're coming to this class on complex numbers. Are you seeing conjugates? Write it there. For the rest of your life, write effect of life there. Whenever a complex number is a root to an equation, its conjugate is also a root. That's effect of life. It doesn't matter whether in Honolulu, Hong Kong, or Japan. Whenever you get a complex number, you identify it as a root to an equation. Its conjugate is also a root. This is like what Deponis says. You buy 1 at the price of, you buy 2 at the price of 1. by 1, you get 2. So when I see 1, I've seen 2. Isn't that beautiful? It looks beautiful to me. If it doesn't look beautiful to you, maybe, I don't know. But that's the fact of life. Whenever a number is a root to a complex number, is a root to a complex, to an equation, its conjugate is also a root. It doesn't happen normally with real numbers. If I've got 3 as a root, that doesn't tell me that minus 3 is also a root of the same equation. Is that right? But once I get a complex number, I know that its conjugate is also a 3. Now, 1 root was 1 here. What is the root? What is the conjugate of 1? The conjugate of 1 is 1, isn't it? Why? Because 1 is on the mirror line. All together. So but you count that as 1. Now we've got how many roots? 1, 2, 3. Now, what I want to do now, I'm not going to discuss this thing with you. I'm going to leave it to you to do it. Take these 3 numbers and multiply this number by itself 3 times and then see whether you get 1. But what is clear is that this number, these 2 numbers have got the same modulus. Check this. This is half plus square root of what? 3 over 2 j. What's the modulus of this? Is half squared plus square root of 3 over 2 all squared. If you put this under the square root sign, what are you going to have? You are going to have 1/4 plus 3/4, which is 1. And you put that 1 under the square root sign, you get 1. So this is actually 1. The square is going to 1. So the modulus of the 3 roots are equal. So in other words, let's have this 1 here. What would you do? Let me do this thing very nicely. I'm promising you to do it very, very nicely. Look at this. This is the vector 1. I hope I'm going to be able to pick it there. There it is. I think it will be somewhere in that direction. That with another vector then. And somewhere in that kind of direction, there'll be another vector. What I'm asking you to do, go and plot these numbers. This number, that number, plot it somewhere there, plot another one somewhere there. You will see that at the end of a good observation, you are going to see that you are going to come up with something like an equilateral triangle around the origin. If you do 5, you're going to get 5 of them around the origin. What are you going to come up with? 5. A pentagon, is it? 5 sides. If you do 6, hexagon. So what are the roots of a complex number? There are vertices of a regular polygon of any size, and all the vertices are equidistant from the origin. Isn't that beautiful? To me, it sounds beautiful. Right not there. The roots of a complex number are mere vertices of a regular polygon of any size. Guys, if I'm not making myself clear, you must say it in capital letters. But I couldn't say it this way if I thought it was not clear. But what is clear to me is not normally clear to anybody else out there, altogether. So you must question it and ask me to say it in different ways or present it differently. Do I need to repeat what I said? Yes. Do I need to repeat what I said? Yes. We calculated 3 roots here. the illustration which I'm showing you here, we're getting 3 vertices, one in that quadrant, one there on the line, and the other one there. I'm saying to you, go and plot those things. What I'm expecting you to do is to get an equilateral triangle around the origin. Then I'm trying to observe with you that if you now calculate root 5, you are going to get 5 points distributed around the origin, and those points are going to generate you a pentagon. If it's 4, you are going to get 4 points. That actually do it. If you want to do it this way, take 1, calculate the root 3. Take 1, calculate root 4. Take 1, calculate root 5. It's easy with 1 because the argument of 1 is very, very easy to determine altogether. But with that process, it will make you feel exactly what I'm telling you, that the roots of a complex number are mere vertices of a regular polygon of n sides. Why n sides? If I'm dealing with root n, I'll get a regular polygon of n sides. If I'm root 2, I'm going root 2, it just gave me 2 numbers. But that's another a polygon. Let's start from root 3 onwards. You get a triangle, a regular. 4 sides. 5 sides. 6, so and so on. Until, if we want, a circle is a regular polygon with infinite sides. Then what do you do? You get infinite points. Because as you increase that 5, 6, 7, you will see that that thing goes towards making up a circle altogether. So when I'm saying, oh, I see, say the man sitting at the corner of a round table. The round table is a circle and it has got infinite corners. Thank you for listening.